a coal mine in Staffordshire, England. Water seeps constantly into the deep shaft, threatening to flood the mine and halt production. Horses turn a wheel that lifts buckets of water, but they can barely keep pace with the flooding. Then Thomas Newcomen's machine is installed, a massive contraption of iron, brass, and wood. Steam enters a cylinder. A spray of cold water condenses it. Atmospheric pressure drives a piston down, pumping water from the mine. The beam rocks back and forth with a rhythmic hiss and clank. For the first time in human history, a machine powered by fire performs work previously done by muscle. The engine is inefficient, consuming vast amounts of coal, but it works. Coal mines can go deeper. The Industrial Revolution has begun. This is the story of how humanity learned to harness steam, a journey spanning centuries from ancient toys to world-changing machines. It's the story of brilliant inventors and patient tinkerers, of scientific breakthroughs and practical improvements, of an invention that would power factories, drive locomotives, propel ships across oceans, and transform human civilization more profoundly than almost any technology before or since. The power of steam was known to the ancients. Hero of Alexandria, a Greek mathematician and engineer in the 1st century CE, described several steam-powered devices in his writings. The most famous was the Aeolipile, a hollow sphere mounted on pivots with two bent tubes protruding from opposite sides. When water inside was heated, steam jetted from the tubes, causing the sphere to spin. It was a toy, a curiosity demonstrating scientific principles, but nobody thought to harness it for practical work. Why didn't ancient engineers develop steam power? Several reasons. Ancient economies relied on abundant slave labor. There was no economic pressure to develop labor-saving machinery. The metallurgy to build strong, precisely fitted cylinders and pistons didn't exist. Mathematical understanding of pressure, vacuum, and thermodynamics was lacking. The coal and iron resources that would later fuel steam development weren't being exploited at scale. Sometimes technologies emerge not because they're suddenly possible, but because conditions make them necessary. For over 1,500 years after Hero, steam remained a curiosity. Medieval and Renaissance engineers built elaborate mechanical devices, clockwork automata, water-powered mills, windmills, but didn't harness steam. Then, in the 17th century, several factors converged to make steam development possible and necessary. European coal mining was expanding. Surface deposits were exhausted. Mines went deeper. But the deeper you dig, the more groundwater seeps in. Flooding was mining's great challenge. Horses and humans could pump water, but inefficiently. A mine could employ hundreds of horses just for pumping. Mining demanded a better solution. Scientific understanding was advancing. The 17th century scientific revolution, Galileo, Descartes, Pascal, Boyle, established principles of pressure, vacuum, and atmospheric mechanics. These insights would prove crucial for understanding steam power. In 1698, Thomas Savery, an English military engineer and inventor, patented the first practical steam-powered pump. Savery's engine had no moving piston. Steam was admitted into a chamber connected to the water being pumped. Cold water was then poured over the chambers outside, condensing the steam inside and creating a partial vacuum. Atmospheric pressure pushed water up from the mine into the chamber. Fresh steam then forced that water out to a higher level. The cycle repeated. Savery called his invention the miner's friend. He demonstrated it to the Royal Society and King William III. It worked after a fashion, but it was limited and dangerous. It could only lift water about 25–30 feet, requiring multiple engines in deep mines. More seriously, it operated at high steam pressure. The boilers frequently exploded, killing operators. Savery's engines were installed in several locations but never became widely successful. Thomas Newcomen, a Devon ironmonger and Baptist lay preacher, improved dramatically on Savery's design. Newcomen understood machines from his ironmongery business. Around 1712, he built the first true atmospheric steam engine, a device that would dominate for 70 years. Newcomen's genius was the separate piston and cylinder. A large vertical cylinder, open at the top, contained a piston connected by chain to one end of a massive oak beam pivoting on a central axis. The other end of the beam connected to a pump rod descending into the mine shaft. Steam at low pressure filled the cylinder, lifting the piston. Then cold water sprayed inside the cylinder, condensing the steam and creating a vacuum. Atmospheric pressure, about 15 pounds per square inch, pushed the piston down forcefully. This drove the beam down on that side, lifting the pump side, drawing water up the shaft. Fresh steam entered, the cycle repeated. The Newcomen engine's beauty was its simplicity and reliability. It operated at atmospheric pressure, no dangerous high-pressure boilers. The parts were large, crude, and easily repaired. It was slow, about 12 strokes per minute, but powerful. A single engine could do the work of hundreds of horses. The engine's fuel consumption was enormous. Condensing steam by spraying cold water into the hot cylinder cooled the cylinder itself, so the next steam charge mostly reheated the cylinder rather than moving the piston. Efficiency was abysmal. Less than 1% of the coal's energy became useful work. But coal mines had abundant cheap coal. Wasting coal to pump water that would otherwise flood the mine was economically rational. By 1733, over 100 Newcomen engines operated in Britain. They spread to continental Europe. They weren't just in mines. They pumped water for city supplies, drained marshes, and supplied water to canals. For the first time, industrial society had a reliable power source independent of water, wind, or animals. But the inefficiency bothered engineers. Coal was cheap at mines but expensive elsewhere. If steam engines were to power factories, they needed to be far more efficient. This challenge would occupy the 18th century's greatest engineers. James Watt, a Scottish instrument maker, transformed the steam engine from industrial workhorse to revolutionary power source. Born in 1736 in Greenock, Scotland, Watt was a skilled craftsman and curious intellectual. In 1763, while working at the University of Glasgow, he was asked to repair a model Newcomen engine used for demonstrations. As he fixed it, Watt pondered why it was so inefficient. Watt realized the problem. Condensing steam by cooling the cylinder wasted energy. The cylinder had to be alternately heated and cooled every cycle, absurdly wasteful. During a Sunday walk in 1765, the solution struck him. Condense the steam in a separate chamber, a condenser, keeping the cylinder always hot. Steam could flow from the hot cylinder to the separate condenser, maintaining vacuum without cooling the cylinder. This insight was revolutionary. Watt's separate condenser would more than double fuel efficiency, but knowing the solution and building it were different. Watt was a skilled craftsman but not wealthy. He needed capital and manufacturing expertise. He partnered with John Roebuck, an industrialist who owned coal mines and ironworks. Watt built experimental engines while working as a surveyor to support himself. Progress was frustratingly slow. Manufacturing precision cylinders was difficult. Watt demanded tolerances far beyond what contemporary ironworkers achieved. Cylinders leaked. Pistons didn't fit properly. Roebuck's finances collapsed, threatening the entire project. In 1774, Watt found a better partner, Matthew Boulton, a Birmingham manufacturer and entrepreneur. Boulton owned the Soho Manufactory, an advanced facility producing metal goods. More importantly, Boulton understood that Watt's engine had revolutionary potential. "I sell here, sir, what all the world desires to have: power," Boulton declared. Boulton and Watt became one of history's great partnerships. Watt provided genius. Boulton provided capital, manufacturing capability, and business acumen. They secured an extended patent from Parliament protecting Watt's design until 1800. This monopoly made them wealthy, but also slowed innovation by preventing others from improving steam engines. Watt's improvements went beyond the separate condenser. He enclosed the top of the cylinder, admitting steam alternately above and below the piston, pushing it in both directions, the double-acting engine. This doubled power output. He added a governor, a feedback mechanism using spinning weights that automatically regulated steam flow to maintain constant speed. This was crucial for powering machinery requiring steady motion. Watt also developed the parallel motion linkage, an elegant mechanical device converting the piston's up and down motion into rotary motion. This was essential. Newcomen engines could only pump. Watt's rotary motion could drive machinery, textile mills, grinding mills, anything requiring rotation. Watt's engine could replace water wheels, freeing factories from rivers. One of Watt's improvements now seems odd. He specifically opposed high-pressure steam. He'd seen Savory's engines explode and believed high-pressure boilers were inherently dangerous. He used only low-pressure steam, just a few pounds per square inch above atmospheric. His engines were safe but bulky and heavy. This conservatism would limit their applications and invite competition once his patents expired. Boulton and Watt engines spread throughout Britain and beyond. By 1800, perhaps 500 were operating. Textile mills were early adopters. Arkwright's cotton mills and others used Watt engines to spin thread and weave cloth. Breweries used them. Flour mills. Ironworks used steam-powered bellows and hammers. The engines varied in size. Some produced just a few horsepower, others over 100 horsepower. The business model was innovative. Boulton and Watt didn't sell engines, they licensed them. Customers paid for manufacturing and installation, then paid annual royalties based on coal savings compared to Newcomen engines. This required monitoring coal consumption, leading to legal disputes. Some customers cheated. Others resented the monopoly. When Watt's patents expired in 1800, competitors flooded the market with improvements Watt had suppressed. While Watt perfected low-pressure engines, other inventors pursued high-pressure steam. This was controversial and dangerous but promised more compact, powerful engines. High-pressure pioneers included William Murdoch, who worked for Boulton and Watt but conducted high-pressure experiments secretly, and Richard Trevithick, a Cornish mining engineer. Trevithick, born in 1771, was a giant of a man, 6'2" and enormously strong, with an inventive genius rivaling Watt's. Working in Cornwall's tin and copper mines, Trevithick knew Watt's engines well but chafed at their limitations. Watt's low-pressure engines were too large and heavy for some applications. High-pressure steam, Trevithick believed, could make engines smaller, lighter, and more powerful. In 1801, Trevithick built the world's first self-propelled steam vehicle, the Puffing Devil. This road locomotive carried passengers up a hill in Cornwall. It worked but caught fire on its second journey. Undeterred, Trevithick built improved versions, including a steam carriage that ran in London in 1803, demonstrating that steam could provide transportation. But Trevithick's most significant achievement was the first steam locomotive. In 1804, he built a locomotive for the Penydarren Ironworks in Wales, betting the owner that his engine could haul 10 tons of iron along a tramway. On February 21, 1804, Trevithick's locomotive pulled the iron plus 70 men riding on the wagons, the first-ever railway journey. The engine succeeded, though it broke the brittle cast iron rails not designed for such weight. Trevithick built several more locomotives but couldn't make them commercially successful. Railways didn't yet exist. The infrastructure, investment, and vision weren't there. Trevithick eventually went to South America seeking fortune in mining, returning to England penniless. He died in poverty in 1833, his contributions largely forgotten until later. George Stephenson succeeded where Trevithick failed, making steam locomotives practical and railways profitable. Born in 1781 to an illiterate colliery worker, Stephenson was largely self-taught. He worked in coal mines, learning engineering through observation and experimentation. By 1814, he'd built his first locomotive, Blucher, for a colliery railway. Stephenson understood that locomotives needed railways and railways needed locomotives. The technology required supporting infrastructure. In 1821, he was hired to build the Stockton and Darlington Railway, the world's first public railway using steam locomotives. It opened in 1825, hauling coal and passengers. Stephenson's locomotion pulled the first train. But the Liverpool and Manchester Railway, opening in 1830, proved railway's transformative potential. This 35-mile line connected two major industrial cities. Stephenson engineered the railway, overcoming enormous challenges, crossing Chatmoss Bog, building the Sankey Viaduct, cutting through rock. The project's scale was unprecedented. In 1829, the Liverpool and Manchester directors held the Rainhill trials to select locomotive designs. Stephenson's rocket won decisively. Rocket incorporated crucial improvements: multi-tube boiler increasing heating surface, blast pipe using exhaust steam to draw air through the fire, and direct connection between pistons and driving wheels. Rocket reached 30 mph, extraordinary speed terrifying to observers. The Liverpool and Manchester Railway was an immediate success. Passenger traffic far exceeded expectations. People discovered they enjoyed train travel: fast, relatively comfortable, and cheaper than stage coaches. Freight moved quickly and cheaply. The railway paid dividends. Investors noticed. Railway mania swept Britain. By 1850, 6,000 miles of track crisscrossed the nation. Railways revolutionized British life. Cities could be miles apart yet connected in hours. Fresh food reached cities from countryside. Newspapers distributed nationally. People migrated to work. Resorts developed around railways. Britain shrunk. Time itself changed. Railways required coordinated schedules, leading to standardized time zones replacing local times. Railways spread globally. America built thousands of miles of track, opening the West. The Transcontinental Railroad, completed in 1869, connected Atlantic and Pacific. European countries built extensive railway networks. By 1900, railways spanned continents: the Trans-Siberian in Russia, railways in India, Africa, South America. Steam locomotives became modernity's symbol. Steam also transformed sea travel. Ships had sailed for millennia powered by wind, but wind was unreliable. You could be becalmed for days or blown off course. Steamships promised scheduled, reliable travel regardless of wind. Early steamships like Robert Fulton's Clermont, 1807, on the Hudson River, proved steam's viability for water transport. But ocean-going steamships faced challenges. They consumed so much coal that fuel for a transatlantic voyage filled most cargo space, making them uneconomical. Paddle wheels, efficient in rivers, were vulnerable in ocean waves. Gradual improvements solved these problems. More efficient engines reduced coal consumption. Screw propellers replaced paddle wheels. Iron hulls replaced wood, allowing larger vessels. By the 1840s, steamships competed with sailing ships on transatlantic routes. Cunard Line's Britannia, 1840, carried mail and passengers on regular schedules. Isambard Kingdom Brunel, Britain's greatest engineer, pushed boundaries. His Great Western, 1838, was the first steamship built for transatlantic service. His Great Britain, 1843, was the first large ocean-going ship with iron hull and screw propeller, revolutionary features proving technically superior. His Great Eastern, 1858, at 693 feet, was 6 times larger than any existing ship, so large it remained the world's longest ship for 41 years. Great Eastern laid the first successful transatlantic telegraph cable. By the late 1800s, steamships dominated ocean travel. Sailing ships persisted for bulk cargo where speed mattered less, but for passengers, mail, and valuable goods, steam was supreme. The world shrank. Voyages that took months took weeks. Immigration from Europe to America surged, enabled by cheap steamship passage. Steam also powered factories, the engine rooms of industrial revolution. Early factories used water wheels, requiring riverside locations and depending on water flow. Steam engines freed factories to locate anywhere, near coal, labor, or markets. This flexibility transformed industrial geography. Cities like Manchester, Birmingham, and Pittsburgh grew into industrial centers. Steam-powered machinery, textile looms, metalworking equipment, pumps, presses, increased productivity enormously. One steam-powered textile mill could produce cloth hundreds of weavers had produced by hand. Steam drove the factory system's growth, concentrating production and workers, creating industrial capitalism and the working class. Agriculture mechanized more slowly, but steam-powered thrashing machines and tractors eventually transformed farming. Steam-powered pumps drained marshes and irrigated fields. Steam drove the modern world's creation. The environmental consequences were profound but initially ignored. Coal combustion released smoke, soot, and pollutants. Industrial cities choked under smog. London's pea soup fogs, actually smoke-laden air, were so thick people got lost and died. Rivers became sewers for industrial waste. Air and water pollution harmed health. Respiratory diseases, cancers, reduced life expectancy in industrial areas. But the economic benefits seemed worth it. Progress required sacrifice. Coal mining expanded catastrophically to feed steam engines. Deep mines were dangerous. Collapses, explosions, flooding, black lung disease. Thousands died annually. Child labor was common, small children working in darkness, hauling coal, operating machinery. The human cost of steam power was immense. Steam also had military applications. Steamships, immune to becalming, gave navies strategic advantages. By the mid-1800s, naval vessels transitioned from sail to steam. Ironclad warships like USS Monitor and CSS Virginia in the American Civil War demonstrated steam-powered iron ships' military potential. By World War I, battleships were massive steam-powered gun platforms. Economically, steam engines were capital-intensive. Building railways, factories, or steamships required enormous investment beyond most individuals' means. This drove corporate capitalism's development. Stock companies, limited liability, and modern banking emerged partly to finance steam-powered industrialization. The social consequences were equally profound. Steam created industrial working class, people who didn't own land or tools but sold labor in factories. Working conditions were harsh, 12-16-hour days, dangerous machinery, child labor, low wages. Workers organized unions, went on strike, and demanded rights. Socialism and communism emerged partly as responses to industrial capitalism's conditions. Steam also created new professional classes: engineers, managers, technicians. Engineering became a respected profession. Technical education expanded. The modern engineer, applying scientific principles to practical problems, emerged from steam engine development. By 1900, steam engines were everywhere: factories, railways, ships, power stations. They seemed permanent. But internal combustion engines and electric motors were emerging as competitors. Gasoline and diesel engines were more efficient, lighter, and didn't require bulky boilers. Electric motors were clean and convenient. By mid-20th century, steam was declining. Steam locomotives persisted longest. The last were built in the 1950s-60s. Some still operate on heritage railways, romantic relics of the railway age. Steamships similarly declined. The last major passenger liners transitioned to diesel in the 1960s. Industrial steam engines were replaced by electric motors. By the late 20th century, steam power was mostly obsolete in developed countries. But steam's legacy endures. The infrastructure it created, railways, canals, ports, remains vital. The factory system, industrial capitalism, modern cities, global trade networks, all trace to the steam age. The environmental and social problems steam created: pollution, climate change, labor exploitation, inequality persist. The steam engine's inventors left mixed legacies. Newcomen died relatively obscure. His engine made others wealthy but not him. Savory's dangerous engines were quickly forgotten. Watt became rich and famous, though his patent monopoly made him controversial. Trevithick died poor despite his revolutionary inventions. Stephenson succeeded commercially and was honored in his lifetime. Their differing fates remind us that genius and rewards don't always align. The steam engine story is ultimately about human ingenuity applied to practical problems. It began with a challenge, draining minds, and ended by transforming civilization. It shows how incremental improvements by multiple inventors create revolutionary change. It demonstrates how technology and society co-evolve. Steam engines changed society, but social needs also shaped steam engine development. From Newcomen's first atmospheric engine rocking above a coal mine shaft to Stephenson's rocket racing at unimaginable speeds to steamships crossing oceans on schedules regardless of wind, steam power conquered distance, time, and human limitation. It turned heat into motion, coal into power, and transformed humanity's relationship with nature and work. The hiss of steam, the clank of machinery, the rhythmic beat of pistons, these sounds define the 19th century as completely as digital chimes define our era. Steam was modernity's sound and its power source. When we ride trains, ship goods across oceans, or visit factories, we travel paths steam engines blazed. The invention of the steam engine wasn't a single eureka moment but a century-long process of insight, experimentation, improvement, and application. It required scientific understanding, technical skill, entrepreneurial vision, capital investment, and social conditions that made it necessary and possible. It emerged when and where it did, industrial Britain, not by accident but because conditions converged. That rhythmic engine Newcomen installed in 1712 didn't just pump water, it pumped the world into a new age, an age of machines, of power from fire, of humanity's unprecedented ability to reshape the material world. The steam engine changed everything. And though we've moved beyond steam to new power sources, we still live in the world steam created.